Uh, Hello everyone. So I was reading this book, Introduction to Electrodynamics by Griffiths, and the second part of the first chapter it deals with gradients and the del operator. So I thought that I would explain it to you people. That why is the gradient the path along which you should go so that you can maximize the rate of increase of your function, which in this case is just our z coordinate, which is a function of x and y. So, right, some context. First of all, what you have is that z is a function of x and y. The gradient of z that's written like this, that's given by this vector. It's partial z upon partial x and partial z upon partial y. This is the x coordinate, this is the y coordinate, and the z coordinate is 0. Right. So we are thinking about finding a vector which is tangent to the surface. Our surface is this thing, x squared plus y squared plus z squared is equal to 100. So basically it's a circle with radius 10. And we want to figure out a tangent to this surface at x is equal to, or I should say x naught is equal to 2, y not equal to 3, and z not equal to, well, whatever this is, like square root of 100 minus what 100 minus 13, right? Yeah, which is like 7, and then you got, I guess, 8. So square root of 87, whatever that thing is, we don't care about that. So at this particular point, we just want to figure out what's the tangent to this thing, such that when you move along the tangent, the rate of increase or decrease in your z coordinate, that's the maximum, or basically just the tangent which is the most vertical, if that makes sense, right? Okay, so the way we'll do that is, first of all, we'll think of what happens when you move in the xy plane by a vector dl or ds, in fact, because displacement is most of the time given by this thing. So this is just equal to dx x hat plus dy y hat. So when you move by this vector from our point x naught, y naught, z naught, basically this thing. So when you move um, with this displacement, what is the change in your z, right? So your dz thing is just given by partial z upon partial x times dx plus partial z upon partial y times dy. This is from the chain rule for multiple variable functions. And this is, of course, just the gradient of z, and that dotted with this vector. So I'm going to write ds vector as this thing. We'll write it as ds, just the length, right? And that times the unit vector. So you can, of course, from this equation write that dz upon ds is equal to the gradient of z that dotted with the direction, so the unit vector. And this thing we want to maximize, so that when you move by the same distance in all directions, we want the direction which gives you the maximum increase or the maximum decrease in your z, right? So the way to do that is that this thing should be at its highest, right? And that, of course, happens whenever s hat, this direction that we're going in, that points uh, that points along the gradient. So it points along this vector, right? And what that would mean is that its magnitude, so dz upon ds for the maximum case, right? I'm not going to write this subscript, so I'm just going to use this because you already know what we are talking about. So this would just be equal to mod of the gradient of z, right? So the magnitude of that vector. So, right, that's the value with which it's going to increase when you move in the xy plane. Of course, this ds thing is in the xy plane. So we can actually form a triangle like this. You have ds as the base, you have dz as this side, and then this vector ds vector is in the xy plane, and ds vector is given by, well, this thing. But remember that your s hat was actually um, it was along your gradient z, and gradient z was this thing. So basically this must be partial z of partial x, and then partial z upon partial y. Well, this thing, but in a unit vector form. So, if you want a unit vector, what you can do is actually do this thing. You can just do gradient. You can just do gradient of z, this vector upon its magnitude, and this times of ds. So that's what this will be. That's our s hat, and this thing is your ds, right? Okay, cool. Yes, so what basically that means is like dx is just equal to the x component of all of this, right? Which is basically just partial z upon partial x upon this thing, and dy would just be partial z upon partial y upon the same magnitude, right? So the final vector that you are getting, so this vector, that is just going to be this partial z upon partial x upon the magnitude of gradient of z, and then partial z upon partial y, once again the same thing. And the last one, so this thing is just dz, but now you know that dz is just this thing times ds, right? Yes. Oh, and by the way, all of this should have ds with it, right? So this is like this times of ds, or we could say dx, right? Yeah, since we only want the x component. Hey, wait a second. Okay, ds is like the length. Sorry. So fine, this times ds, and similarly this times ds. Yeah, I mean that makes sense. Okay, so that's the x component, y component, and then finally the z component is just this thing times ds. So yeah, that's the vector that we want. That's our tangent vector, which is the most vertical. And since we only want a vector and not some certain vector with some certain magnitude, what we are going to do is get rid of these ds things, because yeah, I mean you can divide by the same quantity, right? And this guy's direction is not changing, and you can also multiply by this. So what that means is like you just got this thing. Now of course this can be written like partial z upon partial x, partial z upon partial y, and then this is just partial z upon partial x squared plus partial z upon partial y squared, right? I guess that makes sense. So of course you can do it like this, and you can reduce further as well. So let's go to our case now. In our case, you have x squared plus y squared plus z squared equal to 100, and you're trying to find out what's the tangent or what's the vector along the tangent, right? So just call this as capital L vector or something like that. Yeah, so let's see if this is like going to simplify first, or we can reduce it. And if it does, we'll just call it the simplified form as a L vector. Okay, so you got this thing. Well, just first of all, we just need to figure out what dz upon dx is like. Okay, partial z upon partial x. So keeping y constant, if we just differentiate this thing, you get like 2x dx plus 2z dz is equal to 0. So basically, your dz upon dx, that would just be equal to negative x upon z. So you can put that over there. Similarly, you can put negative x upon y over there. So you got negative x upon z, negative y upon z. And what about this thing? So just square these, add these, you get x squared plus y squared, and that upon z squared. Of course, you can multiply by z, you can get rid of these guys. So you just get this thing. And there you go. This is simple enough. So this will be the L vector that we are talking about. So this is the vector that is tangent to our surface. And of course, you want it at this point, right? So, the vector would be like negative 2, negative 3, and whatever this thing is. Well, x squared plus y squared, right? Well, that's just 4 plus 9 is like 13. 13 upon the z, which is square root of 87. So, yeah, we won't actually write all that because I've just done a more general approach over here, right? You could have any kind of x naught, y naught, z naught over here. It would still work. So that's our L vector. Then of course I can just parameterize the whole line by making a coordinate t. I should not say coordinate, like a parameter t, and just saying L vector times t and the initial point that lies on this thing. So just call this as r naught vector. So r naught vector, the position vector of the point that was initially on the surface, right? That plus this thing, that's our r vector. This represents a tangent, basically the vertical tangent. I'm saying vertical. This is this is like the most vertical. That's what I should say, because it can never be vertical completely, right? It will have some xy component in all cases. Well, yeah, so this thing, this is the line. And of course, that's what I'm doing over here as well. So you have capital L equal to negative x naught, negative y naught, and then the same stuff, x plus y square upon z, right? And I'm using x naught equal to 2, y naught equal to 3, x and z naught equal to all of this, which is in the end square root of 87. Right, now that I've explained all of this, it's time to run this. But for that, first I have to close this. Okay, cool. Now let's run. Let's run our module. It's gonna take some time, so be patient for this. Well, right, so it says that yeah, okay, the square root function is behaving weirdly. That's okay, no big deal. It's still grafted out. So yeah, look at this. Actually, I'm gonna make this full screen so that you can see it better. Right, so look at this thing. I think we should zoom. Okay, cool. Right, so this is our tangent. It really is tangent after all. And yeah, this picture, it shows it all. It is tangent, in fact. Uh, and of course, you can check the coordinates. So where's our origin, by the way? I think, yeah, this is our origin. This is like 0. This thing is 0. This point is, I think it's 2 comma 3. This is the positive one. This thing is also the positive one. So yeah, this is our first quadrant, and then z is positive because it's going up. Yeah, so this is our first quadrant. This is our second quadrant, third, fourth, whatever. Yeah, I guess so. That's the thing. So it's just going up by square root of 87, which is close to 9. It's like between 9 and 10. And then what's the height of this point? Yeah, that looks like it's between 9 and 10. I mean, this is 8 over here, so this must be something like 9, close to it. So right, now you see that this does work. And now I won't have to explain why gradient is the projection of the this thing, like this vector. Why is the projection of that on the xy plane? Yeah. Right, but that's only one interpretation of the gradient. You can also view it as kind of like an operation on any kind of scalar thing. Right. Yeah, it can be used for actual physical quantities as well. Instead of just height, you can have some other thing like potential, and applying the gradient on potential relates it to the field in some way. But all of that is for later discussion. And yeah, I'll be stopping now. So I'll see you guys in the next video.